announce your title. All right, so up next we have a presentation titled Dynamics of Parabolic Flight. I'm sorry, let me start over. Up next we have a presentation titled The Dynamics of Parabolic Flight and Passenger Perceptions.
All right, just 1 second, and thank you everyone for your time today. Let me get this in presentation mode, and off we go. And I'd just like to confirm just beforehand, everybody can see my screen okay?
Yes.
Okay, very well. Everybody, my name is Jackson Collins. I am an aeronautical engineering and professional flight technology student incoming to Purdue University this year. My project today is based off an airplane that NASA flies for conducting zero gravity flights, and they fly in this cool pattern. My project title is Dynamics of Parabolic Flight and Passenger Perceptions. So we have an astronaut that is floating in midair.
Wow, there's nothing.
This astronaut said, wow, there is nothing like this. The euphoria that she's feeling in this airplane is incredible. Now, let me just preface one question to you.
Where is she?
At what point in the flight
Kelly.
will this astronaut become weightless?
Yeah.
And while we're flying in this trajectory, there are some important things to consider.
No.
Now, just ponder on it just for a bit. So, it led me to ask a couple of research questions. The first one is, what forces do passengers experience during the parabolic arc flight? So the astronaut that you saw in the video, why does she feel so euphoric and happy? But let me preface that a parabolic arc is essentially U, but it's upside down. It's an inverted U. And the airplane follows this trajectory in which the passengers, like you saw, well, in the first video, become weightless. And I wanted to record 3 different dimensions in which accelerations occur on a flight simulator. So I want to know that while riding this parabolic arc, did the astronaut that you saw in the first video get flung into the cockpit, or was she pancaked in the ceiling because the airplane was in all kinds of attitudes? And the simulator will report the acceleration factors. So as I want to say, there's a frame of reference to consider in this airplane. NASA flies an anti-gravity machine in which space station astronauts train for zero-G flights in preparation for living in outer space, or perhaps in the space station. And all zero-G means is the point in which the astronaut you saw in the video becomes weightless. So in the 5 seconds that you saw the astronaut say, wow, this is so cool, she had fallen 400 feet. And almost in a subsequent 5 seconds, she's going to fall almost 3 times that, 11 or 1,200 feet. And so part of my engineering interests are to examine the stress being imposed on the aircraft's wings. The aircraft's wings will bend and flex when it is pitching up and down at different stages of the arc. So here are some constraints to consider. The pilots that are flying this airplane don't want the wings to split apart. So the airplane that you see here, this is an A380. Unfortunately, I don't have a model like the 737. But what I want to show you is that the airplane in the arc can climb so steep that if you were to weigh 200 pounds, you would feel like 800 pounds of force, that is 4 times 200 pounds, will make you feel like your tush is being held on the bottom of the airplane. And conversely, if I were to pitch the airplane down, it would almost feel like you're standing on the ceiling of the airplane. So any steeper up or down, the airplanes could fall apart. It's under so much stress. So unfortunately, I just kind of gave you the answer away. When you stand on the ceiling, as the airplane is in the downstage of the arc, she becomes weightless. So the free fall should occur vertically. As Sir Isaac Newton once said, what goes up must come down. Everything will fall under Earth's gravitational attraction. And lastly, while the airplane is descending, the airplane shouldn't hit the ground. So my initial enthusiasm. You see your astronaut here blowing a water bubble in on a space station. I thought to myself, what if I were to take an airplane, the one that I fly, which is, a small, tiny, fraction of the size of this thing, and maybe squirt some toothpaste or a water bubble like you saw the astronaut here in an airplane that I fly. Well, unfortunately, reality dashed my hopes. The airplanes that I fly are too slow. So this airplane you see here can fly at 600 miles an hour. So it can withstand a lot of forces. but the airplane I fly can only fly 160 miles an hour. So all of a sudden, as soon as I'm pitching the nose over to try to kind of float out of my seat, all of a sudden I reach the max speed. And in theory, what the engineers say is that, hey, if you were to recover and exceed that max of that 160 mile an hour speed, the wings could break apart. And so I wanted to conduct a simulation. I thought to myself, well, what happens if I don't listen to the engineers? Unfortunately, I can't show you the exact full screen because that will cause some inherent delay and lag in the computer. And I hope the video is continuous here. But you can see here that I'm pitching up in the upstage of the arc. You see that there is a blue figure in the top left corner. And I will show you what that is in a later slide. But it's articulating the G-forces in the 3 dimensions in which I'm flying. Am I crushing my passengers at the ceiling of the airplane? Or is the astronaut, like you saw in the first video, floating and maintaining, the flight in one area? And as you see here, all of a sudden I'm pitching down faster and faster. And what you see here is the Pacific Ocean in Point Reyes. And you see that there's a control wheel moving. That control wheel is the equivalent of steering in a car, like the steering wheel in a car. I can pitch up, but what happens if I pitch up too much? The wings are starting to flex. All of a sudden, I'm pitching up so hard, my instrumentation went dark. What's happening? Well, unfortunately, the plane broke apart. And the lovely Point Reyes that you see that's coming faster and faster will have a smoking hole in it. So I thought to myself, well, what if I were to conduct another simulation? And unfortunately for time constraints, I can't show that, but I have linked a YouTube video in the sections below so you can see the successful attempt. So here's the shape of the trajectory that I flew this airplane in. As I pitched up, there is not a lot of G's. I mean, you're in your seat, but as the aircraft is still climbing and begins that 0G pushover, hence the floating, that is when she says, wow, that was so cool. I can't believe this is happening. And all of a sudden I'm descending so fast and I have to pull back again. And so I'm flying this sort of snake-like pattern. So here is the perception. This is the frame of reference. The astronauts are the ones that are floating in midair. They can't see anything out the window. All they know is that they are floating. But the pilots, they're the ones that are free falling. They are saying, hey, I don't want to be a smoking hole. I want to pull up and make sure I don't crush my passengers. And so that you see they have a little bit, and for the faint-hearted, it may be a little disconcerting for what the pilots have to do. So my recommendation would be have fun and hang out in the back. So let me distinguish some nomenclature here. Weightlessness, the passengers perceive weightlessness, the point in which we float, is when the airplane is in free fall. When you see these pilots pitching down and they're floating, that is what they perceive to be weightlessness. So imagine if I were to take a lead weight, 1,000-pound lead weight, at like 40,000 feet. I'm going to drop it. It keeps getting faster and faster. It's falling under Earth's gravitational attraction. It's exactly what's happening. The airplane is falling faster and faster as they are free floating. And so some observations made. Flying while emulating the point in which passengers float, the 0Gs, is very sensitive. You saw the instruments go dark and the plane is smoking fireball. That's what happens if I pull back too much. And so when I begin this...
2 minutes, sorry to interrupt, 2 minutes.
No problem. The 0G begins when the aircraft's nose is still pointed high in the sky and begins to pitch down. So it's very hard. So here are the important dynamics and constraints. This gentle curve that you see here was what the simulator reported. I wanted to replicate that upside down U. And sure enough, I did. And as you see on my secondary graph, everything is sort of expressed in meters and seconds for the sake of civilized measurements. And the top number you see on the left here, the 4, that shows you that that's the point, that is a magic number that we can't exceed, or else in theory, the wings will break apart. So I pitched up and pitched down, and I have accelerations here that you see that really maintain 0. And so they didn't get flung out the wing exits, they maintained their position, which was floating in space. So here is the accelerometer that you saw, the G-force detection system. I apologize for the somewhat obscure image, but it shows you the 3 dimensions of acceleration, the 3.5 Gs, the -6 or 7,000 feet per minute down, and so forth. So I wanted to model altitudes. I wanted to say, well, if the simulators report that arc, what if I use piecewise summing, physics, and I will link the description of how I calculated that, of replicating that upside down U, that parabolic arc. And you can see that it's very close. And the disparity, there's a gap between there, and I want to know why that occurred. Same thing with velocity. Why did that occur? That gap. So I modeled the acceleration from the simulator and with hand-drawn calculations. So for further study, I want to understand why our model of the simulator's altitudes and functions of time and speeds disagree. There's about a 20% gap. Why does that occur? The fun continues. Please see my calculations for those that are interested. And here's a take-home message. What is one man's weightlessness, like you see in the left image, is another man's free fall. While they're floating, someone's falling. Thank you so much for your time, and I'd like to acknowledge my friends for letting me use their simulation software.
Thank you, Jack, for another enthusiastic presentation. That was wonderful.